Good morning, Lucy, Sophia, and Jack. Do you think Jack's going to watch this?
No.
Do you think Sophia's going to watch this?
Probably.
Yeah,
Do you think Lucy's going to watch this?
definitely.
Okay. Did you hear what your friend said?
Yeah, she'll be watching it. Just
All right, practice test. We're going to go over. Look at number 4. Does everybody have it out? There's a picture. The horizontal turntable shown above rotates at a constant rate as viewed from above. A coin on the turntable moves counterclockwise in a circle. Which of the following vectors represents the direction of the frictional force exerted on the coin by the turntable when the coin is in the position shown? That's at the top of the circle. Okay, so what did you put for that, Tony? As in cat?
Yeah.
How many put cat? You are correct if you put your hand up. The frictional force is pointing toward the center of the circle. There's the coin, that's friction. There's the force of gravity, which in this orientation is into the board, and there's a normal force which is out of the board, but the only force in the plane of the board is friction, and that's toward the center of the circle. So that's down. C. Number 20. An astronaut in an orbiting spacecraft attaches a mass m to a string and whirls it around in uniform circular motion. The radius is r, the speed is v, the tension in the string is F. If the mass, radius, and speed are all doubled, what would happen to the tension? What do you think about that, Steve? Did you say cat? B, boy? How many think it's B, boy? Raise your hand. Raise your hand, two out there, but it's not B. I'm sorry, Steve. B is a good guess, but several people put something else. Lily, what did you put?
B.
You put B, I'm sorry.
Yeah.
You're changing your answer now? You can do that. Okay, what do you think it is now, Steve? C? How many think it is C, cat? Because Steve looked over at Nate's paper. I don't know what you did. I don't know. I just made that up. I'm sorry. Just kidding. C is correct. All right, this is where you simply say centripetal force is mv squared over r, and the centripetal force is the tension. Okay, so if you double everything, then the mass is twice as much, the velocity is twice as much, but that's squared, and the radius is twice as much. And if you calculate that, you get 4, don't you? So the tension has to be 4 times as much because the right side of the equation is now 4 times as much. Everybody see that? 2 squared. Okay. Yeah, if you put B, you probably just forgot to square the velocity. All right, I'm on number 26. A 4 kilogram mass is attached to one end of a rope, 2 meters long. If the mass is swung in a vertical circle from the free end of the rope, what is the tension in the rope when the mass is at its highest point if it's moving with a speed of 5? All right, what did you have for this one? Jaden?
B.
How many put B, boy? See, you're getting them right. B is correct. This is where you need to know for the vertical circle that when the object is at, now I'm using the same circle, but now it's a vertical circle, when it's at its highest point, then the forces on it are tension and mg, and they're in the same direction, so tension plus mg is equal to centripetal force mv squared over r. Okay, if you set it up that way, you'll get it right. 27. A ball of mass, is everybody okay with that last one? Do I need to do the math? Are we okay on that? Okay, 27. A ball of mass m is fastened to a string. The ball swings at a constant speed in a vertical circle of radius r with the other end of the string held fixed. Neglecting air resistance, what is the difference between the string's tension at the bottom and at the top? What do you have for that, Erica?
I got C.
Erica says C. How many think the answer is C as in cat? Is that what you said?
Yeah.
Cat. Put up your hands. Several of your friends are thinking about putting up their hands, but C is not right. I'm sorry.
Yeah.
So I'm now switching over to Claire. How many think it's B, boy? You are correct. In this case, it's the difference between up here and down there in a vertical circle. Well, up here, the tension and mg are in the same direction. Down here, the mg is still down, but the tension is up. And the tension has to be a lot greater because it's winning. And so the difference then, here you go. The question is the difference in the tension. Okay, so up here you have tension plus mg is equal to mv squared over r. Here you have tension minus mg is equal to mv squared over r, same thing. And so the same thing over here, m and v and r are the same. And you need to, I'll write it to make sure I'm making the point here. Since they told you the speed is not changing, then you know m and v and r are the same. So whatever that number is, it's the same at both places. All right, so if you solve it for tension, here you get that number, whatever it is, minus mg, when you move the mg over. And here you get that same number, whatever it is, plus mg, when you move the mg over. Okay. So the difference is, the question is, what's the difference in tension? That number is the same, so the difference up here, they're subtracting mg. Here they're adding mg. I hope you can look and see, then that difference would be 2 mg. The difference between that and that. Does that make sense? All right. Come on the next page, which is the free response problem. You have a coin on a turntable again. That's a fairly common physics question for circular motion. Put a coin on a turntable. All right. A asks you to draw vectors. This is not a free body diagram, that's forces. The question in A is draw the vectors showing the linear velocity and the instantaneous acceleration. So there's the coin. Well, here's the circle, and the coin was over here. When it's over here, and this is looking down at the turntable. You know, this is not a vertical circle. This is a horizontal turntable. All right. So the linear velocity, if indeed the circle is moving in that direction, counterclockwise, then the acceleration, first of all, is always toward the center. The linear velocity, though, is tangent to the circle. So on the penny, or the coin, whatever it is, that would be that. So that's what you had to do, is draw them perpendicular to each other, where on this drawing, the velocity vector was straight up, because that's tangent to the circle. And the acceleration vector was toward the center of the circle. And they had to be labeled V and AC. That's part A. So I didn't ask anybody what they got there, but I'm just showing you that's the right answer to A. Any questions about that? All right, B. Now we want to know what's the linear speed of the coin. So tell me what you got for that coal. What do you have for part B?
5.33.
That's a bit too much. Maybe your decimal point's in the wrong place, but I don't know. It is 0.5 something. Anybody get 0.5 something?
Yeah.
So tell me what you have, Sarah.
0.59.
0.59 if you round it to 2 digits. Meters per second. Okay, that should be, just based on the information you have, really the only way to work that is that velocity is 2 pi r divided by the period, that equation. And it told you the time to go around once was 1.5 seconds, so that's the capital T. And then the radius is 0.14, it gave you that as well. So that you can use those numbers to calculate. All right, that was part B. Part C, The rate of rotation is increased. The coefficient of static friction between the coin and disc is 0.5. Now determine the speed of the coin when it just begins to slip. Now before it slips, what's holding it there?
Friction.
Static friction. Okay, so if I erase my acceleration and velocity vectors, now if I draw force vectors, the force of friction is what's pointing toward the center. And that's the only force on it in the plane of the board. Its weight is in and the normal force is out. But friction is the only force that's parallel with the plane of the board up here, and that is toward the center, so that's centrifugal force. Okay, when it just starts to slip, that means the static friction is maximum. It's at the most it can be. And you remember, for static friction, the most it can be is mu s times the normal force. That's its maximum. Well, the way we learned that equation was greater than or equal to. Well, the maximum is when it's equal. Okay, so you're thinking of it that way. And so friction, static friction is equal to mv squared over r. Okay, so what answer do you have for part C? Tony, what's your final answer?
I got 0.83.
0.83, anybody else get that? That is correct. And I think you'll get that if you simply take this equation, and for static friction, plug in mu times the normal force, but the normal force, remember, is equal to mg. It's a horizontal disk, and so the up has to equal the down. So in place of normal, you can put mg, and that's equal to mv squared over r. The m's cancel. And you know what mu is, they told you. You know what g is, 9.8. And you know what the radius is, they told you that. So you solve this for v. And that will give you 0.83 meters per second. All right, part D. Any questions on C? All right, part D. If the experiment were repeated with a second identical coin glued to the top of the first, so you've doubled the mass, but everything else is the same, how would your answer in part C be different, Erica?
I said, this may be wrong, but I said it wouldn't do anything because the mass is increasing, but it ends up canceling out.
It would make, you are correct, it would make no difference. How many of you put it would, not the explanation, but the right answer is it would make no difference. That's correct. The answer to part C would be the same. That when you solve this for velocity, it'd be the same, and you can even look at what I've written up here and mathematically see why that's true. You double the mass, doesn't matter, the m's canceled out, didn't they? And you can say that in your explanation. Better explanation is when you get conceptual rather than just the equation, but still it's true. I know that because the m's cancel on the equation. Now, the conceptual answer would be, if you double the mass, that's going to double the centripetal force over here. So the mv squared over r is centripetal force. But that's also going to double the friction because there's an m on both sides. Therefore, it would take more friction to give it more centripetal force. So it all works out the same. Yes?
Could you say like the mass doesn't affect the x component of acceleration? Because it's a y component?
You're talking about this because it's horizontal?
Yeah.
At that instant, there is no y component to acceleration, it's all x.
Yeah, that's why mass doesn't affect it.
And so that's a true statement. I don't know if that would be, I'd have to think about it, whether that answers, it really justifies. Well, it's a true statement though, so it probably does. Okay. Also, you know what else? If I was going to just answer it mathematically by saying the m's cancel out, it would be a better idea to also include the reason. See, the question is why is v the same? And the answer is yes. And so it would be better also to say, not only did the m's cancel out, but mu is the same, g is the same, and R is the same. Now, you already knew that, but if you don't write it down, the grader doesn't know that you realize that's true. Because if any of those things change, then it's still not the same, is it? So you point out, it's the same coefficient of friction, it's the same 9.8, and it's the same radius of the circle. So none of that changed. The m's cancel out, v has to be the same. Does that make sense? All right, focus questions. Open your books because you don't know what the questions are. You didn't write them down. So open your book to the end of chapter 5 and have your answers out. It's on page 155. Page 155. We're going to go over these focus questions in the time we have left, which is... Sarah, when do we get out of here today? All right, we still have 15 minutes. This is great. Number 1. 2 cars are traveling at the same constant speed, v. Car A is moving along a straight section of the road while B is rounding a circular turn. Which statement is true? All right, Minho, what did you say for number 1?
C.
Did you say C as in cat? Anybody else put C? You are all correct. They're moving at the same speed. Neither is speeding up or slowing down. B is accelerating because it's turning. It's centripetal acceleration. All right, number 3. 2 cars are driving at the same constant speed v around a racetrack. However, they're traveling through turns that have different radii, as shown in the drawing. Which statement is true about the magnitude of the centripetal acceleration of each car? What is true? Jaden.
B.
Did you say B is in boy? Boy? How many put B as in boy? You are correct. B says the magnitude of the centripetal acceleration of car A is greater than that of B. It's greater because, Jaden, why?
Because the radius is smaller.
Radius is smaller, exactly. Centripetal acceleration is v squared over r. You need to know that tomorrow. And you can easily see these are inversely proportional. So if r is less, a would be more.
I remembered that.
Excellent. Okay.
Got it.
Number 7. The drawing shows 2 identical stones attached to cords that are being whirled on a tabletop at the same speed. The radius, now this is on a tabletop, so the objects are going around in a horizontal circle, like on the top of a table. All right. How is the tension T1 in the longer cord related to the tension T2 in the shorter cord? All right, Kyle, what did you put for 7?
D.
How many think it's D as in dog? You are correct. If you're raising your hand, D says T1 is half as much as T2, and that's because this tension, they're calling T, is mv squared over r. Remember, it's a horizontal circle, so the thing's moving like this, but this is looking down at it. It's not a vertical circle, it's horizontal. So the only force pointing toward the center is the tension. All right, so it's as simple as that to think about. If the radius is twice as much, tension has to be half as much, because the m and the v are not changing. Okay. I'm on number 8. 3 particles have the following masses and speeds and radii. Okay, so there's a chart showing that. Rank the particles according to the magnitude of the centripetal force that acts on them largest first. All right. Nate, what did you put for number 8? Nate, what? Did you say A, as in apple? How many think it's apple? You are correct. Steve, what did you think it was? What did you get for number 8? A. Well, raise your hand. Oh, let me do it again. How many put A for the answer? Yes. You put A. Almost all of you put A. Excellent. Now, here's what you do. Remember, centripetal force is mv squared over r, isn't it? So take the numbers they give you, like number 1, where m is 1, but v is 2, and r is 1. So you go over here and you do that. M is 1, v is 2, but that's squared because it's v, and r is 1. And so you calculate that and you get 4. And you can just do that with the others as well. If you do the second one, it comes out to be 3, and the third one, it comes out to be 2. So that's the greatest, that's the middle, that's the least. Okay, let's look at number 10. There are 2 identical cars. When it says identical, you know their masses are the same. One on the moon and one on the earth, and they have the same speed and are rounding bank turns that have the same radius. So same mass, same speed, same radius. There are 2 forces acting on each car, its weight and the normal force. And when they tell you that, you realize there's no friction. They said there are only 2 forces acting on it, the weight, mg, and the normal force, no friction. Recall that the weight of an object on the moon is about 1/6 of its weight on the earth. How does the centripetal force on the moon compare to that on the earth? So tell me, Lily, what you got for 10?
I'll put B.
How many think it's B, boy?
I don't think it's right.
Most of your friends are agreeing with you, but I'm sorry, B is not right. Tricky question, isn't it? If I tell you B is not right, who has something besides B? Minho, what did you put?
A.
How many think A is right? There are 2. Is your hand up, Sarah? Sarah's hand's up also. There are 3 of you, if you count Sarah. A is correct. Now we need to look at this. What in the world? A says the centripetal forces are the same. Here's why. Well, here's the easy way to answer it. If you don't think too much. Sometimes that is easier. Don't think too much. If I don't think too much, I get this. Centripetal force is mv squared over r. It didn't ask about weight. It didn't ask about normal force. It just asked about centripetal force, right? Well, that's mv squared over r. Which one had a greater m? They're the same. Which had a greater v? They're the same. Which had a greater r? They're the same. Those have to multiply to be the same answer. That's the way to get it without thinking too much. Now, if you do start thinking, though, you say, okay, it's a bank track. Here's my car. One's on the moon, one's on the earth, and I've got this and this. Oh, this weight's going to be a lot different on the moon, be a lot less on the moon than it is on Earth. So therefore, the normal force is going to be less, and I know this component of normal force pointing toward the center of the circle, that's equal to the centripetal force, and that's less. So you'll start thinking, well, it's got to be less on the moon. Did you think that way? If you missed it, did you think that way? Here's the reason that doesn't work out, because it would be. If everything else was identical, this would be less, so centripetal force would be less. But the one thing it didn't mention was theta. It did not say they were banked at the same angle. And in fact, if all this was the same, the angles would have to be different. Okay, they would have to be different, or else they wouldn't be going the same speed without friction. Some of you memorized the equation G tangent theta equals V squared over R, which works for a bank track. And if you look at that, then you would realize, well, if V and R are the same, but G is different on the moon. It is. It's not 9.8 on the moon, see? Theta has to also be different. So they would have different angles, or else the rest of the question wouldn't work. But given what you were told that MV and R have to be the same for both, then centripetal force has to be the same. All right. You get that now? You can't just assume when it says they're both on a bank track, it did not say they're at the same angle bank track. Okay. Now I'm on number 11. Two identical satellites are in orbit about the Earth. One orbit has radius r and the other's 2r. There's a picture there. The centripetal force on the satellite in the larger orbit is blank as that on the smaller orbit. What do you have? This is the, what's the actual question? The centripetal force, that's the question. Okay, so tell me, Kyle, number 11, what do you have?
D.
How many think it's D? Half is great. Several people put D, but I'm sorry, that's not right. What? Who has a different answer? Jaden, what do you have?
E.
Did you say E as in egg? Anyone else put E? E is correct.
Why is it incorrect?
That's crazy. That's not true. What do you ask us these questions for? All right, look, the satellite. Here's the Earth, here's the satellite doing this. What's the only force acting on the satellite? Force of gravity. Okay. Force of gravity then is equal to centripetal force, isn't it? I forgot the question again. No, what is, centripetal force is the question. Okay, if you just realize force of gravity is centripetal force, then it's asking you about this, but that's the same as this, isn't it? Well, this is G_m over r squared, isn't it? That's force of gravity. That's the equation you learned some time ago for force of gravity. And so the masses are the same. One satellite was here and one was up here, right? Twice as far away. Well, the difference is r, but in this equation is r squared. That's what makes the answer. This one would be 1/4 as much because it's divided by 2 squared. That's just one radius, so that's divided by 1 squared. That's 1. That's the r is 1. Here the r is 4. So up here it's 1/4 as much. Yes.
Okay, why couldn't you use the centripetal force equals mv squared over r? Because then r is not squared.
Okay, good question. Their r is not squared, but these two satellites don't have the same speed.
Oh.
They don't. This one would be going slower. And in fact, it would be going, what if they ask you how much slower is it going? I don't know. We could figure that out too. Probably half as much speed, wouldn't it? Or maybe 1/4. I don't know. We could do the math. But the reason you can't use it here is that the V's aren't the same. Yeah. Over here, everything is the same except the R. Okay. And if you remember the satellite equation, V satellite is equal to square root of GM over R. That's a good thing to remember about satellites, but none of that applied either because the V's are different. If the V's were the same, then again you could look at this, but the V's weren't the same. The speeds were not the same. Okay, look at number 15. The drawing shows an extreme skier at the bottom of a ski jump. At this point, the track is circular with radius r. Two forces act on the skier, her weight and the normal force. Just two forces, so no friction again. Which relation describes how the net force acting on her is related to her mass and her speed and to the radius? So you're looking at the choices, picking out the equation that would apply. All right, what do you have as an answer, Nate, for number 15? B is in boy. How many put boy? You are correct. So all of you raised your hand, I think, so we won't go over that. The normal force is up and the mg is down, so that's why it's normal minus mg. And that's equal to centripetal force. All right, we are through going over the homework. Who has a question about your test tomorrow? Anything about this unit?
Can you just give us the?
As far as things you've learned, what are you about to ask me? Were you about to ask me a question?
To ask you if we could have the answer sheet for tomorrow's test.
Okay, yeah, I'll run that off for you. The new things, you already knew force of gravity, didn't you? G M over R squared. The new thing is that centripetal acceleration is V squared over R. And so centripetal force would be M V squared over R. And centripetal force could be a number of things. We've talked about it being friction, it could be the tension in a string, it could be gravity. Okay, so, but whatever's pointing toward the center of the circle is the centripetal force, and that's always going to be mv squared over r. Did you have a question, Kyle?
What's the constant gravitational constant?
I would give you that. It's 6.67 times 10 to the negative 11. But that would, the constants you'd always be told. All right, so basically that right there is what this chapter 5 is about. And we looked at a lot of different situations where you put different things here for centripetal force. Okay. All right. Any questions, comments, thoughts? Bell's going to ring in about 1 second.
Wow.